Welcome to Season 3, Episode 6 of the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting from the campus of the University of North Dakota here in Grand Forks, North Dakota. We do have a live chat that is running today, so if you feel free to send us a question or some comments, we'll keep an eye on that. Also, as a disclaimer, Robert.
Oh, yeah.
Do you want to do this one?
The opinions expressed are just those of myself and Wayne and our guest. They are not in any way associated with any other entity like the University of North Dakota or the state of North Dakota or any of that. So just us.
Just us. So today we have a very special guest.
Yep.
Do you want to do the intro on this?
I can, except I'm drawing a blank at the moment.
Okay,
I know his name.
Let me do it then, Robert. You ready? Okay, I'll do it then. So
Okay.
you're drawing a blank.
All right.
Our guest is Dr. Nicholas Scott, who is the telescope system scientist for the CHARA array. So, Nick, thank you very much for doing this.
Yes.
Sure. Thanks for having me. Good to see you guys.
Especially since he's coming in from Los Angeles.
I'm in Los Angeles. Yeah. So the CHARA array, CHARA stands for the Center for High Angular Resolution Astronomy. So CHARA is a center of Georgia State University, founded quite a while back by Hal McAllister. And as part of CHARA, what they decided to do was build an interferometric array. And so that's a bunch of small telescopes that you can hook up together to simulate having one giant telescope. And they built this on Mount Wilson, which is just outside of Los Angeles, California.
Right.
So my commute's about 40 minutes up one of the most beautiful and dangerous roads in the country.
Having driven that road, I can verify this.
Now, I have to ask you something since you mentioned it. How close were the recent fires to Mount Wilson?
1,000 feet.
Wow.
The between the most recent Eaton fire, which also threatened both my house and then my work. So that was a very bad week. Thankfully got out lucky. We got very lucky, and a lot of people were not nearly as fortunate. Many people we know lost their houses. Altadena is gone basically as a city. It's really tragic. But yeah, the fire came up. What saved us was that it came up the ridge, and the wind was steady from the other direction, and that kept, once it hit the top of the ridge, that kept the fire still stalled for enough that firefighters could really come in there. And they were stationed actually on Mount Wilson. They have a tank of, I think, 250,000 gallons, maybe 500,000, and we have our own tank of 500,000 gallons as well. So we have water up there. But we lost power for a bit, and so that couldn't power the pumps. It was a whole ordeal for days, and we were just kind of nail biting the whole time. But no structures were damaged of the array or of the historic Mount Wilson Observatory. We got real lucky. And between that fire and the past two in the past 15 years, the station fire and the Bobcat fire, all sides of Mount Wilson have burned. So we're actually in good shape for the future because there's no more fuel. This was the last area that hadn't burned in, I think, 100 years.
Okay. That's kind of crazy in and of itself.
Yeah.
Wow. So, yeah, I remember I think it was the station fire. You actually took some damage at the array.
Yeah,
So-
I think some of our internet infrastructure, a few other things got burned.
All right.
So it was also a close call.
I remember people talking about on our shared mutual friends were talking about they were lucky that they weren't sure they didn't get any smoke or anything else in the vacuum lines, which we will discuss in a little bit. But
Just thinking about other fires. I mean, Kip Peak almost got wiped out not long ago as well.
Yep.
And I know there was a famous one in Australia a few years back, which did take out one of the older telescopes and some instruments that scientists were working on down there as well. Very expensive type of stuff.
Siding Spring, I think.
Yeah, that's right. So I knew they built a whole new telescope. The Sky Mapper survey is done from that new telescope now. So that was the Phoenix, if you like.
right.
Yeah,
Rising from the ashes, unfortunately.
yeah.
Yeah, it kind of goes with, I mean, where you build an observatory is often somewhere real remote, usually, forested up on a mountaintop and near the ocean. And you get some nice still air, but it also means you get a lot of air to fuel fires.
Right.
Yeah.
And so I guess we'll dive on into things.
Yeah.
We've mentioned interferometry. We've mentioned it on the show before. But, Nick, you are an expert at this, so I'm going to ask you to explain what interferometry is, how it works, and why we like it.
Sure. Well, the first stumbling block you just hit is the saying it. Interferometry. It catches people every time. It's just the science of interference, because and it all goes back to light. Light has wave-like properties. And if you think of, dropping rocks on a pond, the ripples travel and you can get waves crossing over each other. And when they cross, you get constructive interference and destructive interference from that wave pattern. And we can do the same thing with optical light, the stuff we see. Let me pull up. I've got some slides to show that'll make it a little easier. And if you're just audio, I'll describe what I'm doing too. Let's see if I can get this bigger before I share.
Okay.
All right.
When you're ready.
Yep, doing it now.
Okay.
How's that?
Beautiful. Oh, yeah, that looks nice.
So this is just Mount Wilson. I just wanted to show like where we're at. And, it's kind of a really unique site in the world. This is the same site. That's the 100-inch telescope. This is the same site, and that's Hubble down there looking through the eyepiece, kind of collaged into the actual telescope he was using. This is the site where Shapley and Hubble and Humason and all of these things were done at Mount Wilson. So it's a 100-year-old, over 100-year-old observatory. Really an amazing site. If you're ever in the Southern California area, it's worth coming up. It's open to the public. You can come walk around and see this. But this is what people picture when you say you're an astronomer. And I constantly have to tell them that, like, yes, that's great. Our newest telescopes were not built in a shipyard with rivets, though, and we don't use our eyes. We use state-of-the-art cameras.
Right.
Unfortunately, this is an example of a more modern telescope. This is one of the ones I've worked at. This is I believe this one's Gemini North. They're twins. They're Gemini North and Gemini South. And you see this. You've got people down here for scale. This is an 8-meter class telescope. So this is a massive instrument, single monolithic mirror. So just one big piece. And this is what most astronomy is done with if you're not doing stuff from space. But the mirror is only 8 meters across. And in astronomy, what matters for seeing small details is the width of your mirror. The bigger your mirror, the wider it is, the finer the details you can resolve. We call that angular resolution. So there's all sorts of these large telescopes. And we're now in a really unique time where extremely large telescopes are being built. A small aside, don't ask astronomers to name your kids ever. We name things like telescopes like VLT and ELT. That's very large telescope, an extremely large telescope. If we named your kid, it would be like very small human.
I like that, though.
We've got TMT, the 30-meter telescope, GMT, the Giant Magellan telescope. So these are all projects underway, all trying to build bigger and bigger telescopes. And these extremely large telescopes will be 16 times sharper than the Hubble Space Telescope. But CHARA, the array itself, is 17 times sharper than any of these extremely large telescopes. Because what we do is we don't have the sensitivity. We're not taking a big bucket to collect all this light, but we're kind of doing cookie cutters on a simulated giant mirror and getting the width of this giant telescope.
Okay.
So the main reason is building one of these giant telescopes is extremely difficult, extremely expensive. So like a 30-meter telescope collects 150 times the amount of light that we collect at the CHARA array, but it also costs 150 times more.
Right. And that's the big deal is these giant telescopes are in the order of billions of dollars to get up, and then you've got to operate it. Whereas CHARA, you're dealing with what, 1.5 meter telescopes?
Just 1 meter telescopes.
1 meter
6
telescopes.
of them. CHARA costs less than a fighter jet.
There
One
we go.
fighter jet.
There we go.
So when I talk about angular resolution, what I mean is the small details you can see, right? Like you think of like the resolution of your computer screen or your TV, the high resolution, the better the little details. And it's the same thing in reverse with the telescope. The wider your telescope, the bigger the diameter of your mirror, or in an interferometer, the bigger the separation between your telescopes, the smaller the details you can see. So like your human eye, it can resolve what's called an arc minute. So if you break down degrees, minutes, seconds for units of angle, you can see what we call an arc minute. There's 60 arc minutes in a degree, and there's 60 arc seconds in an arc minute. Goes like that. An arc second, which is the smaller than the arc minute, that's about the width of your hair at arm's length. So pluck out a hair, hold it at arm's length. That's an arc second. What we measure with the array are things that in the order of like milliarc seconds. So that's like taking a $50 and looking at it from 4,000 miles away.
That's crazy.
And we're starting to get into our next generation of upgrades, looking at things on the order of tens of microarc seconds. So a microarc second, so it's 1,000 times less than a milliarc second. With that resolution, you could resolve the period at the end of a sentence on the mission manual of the Apollo spacecraft left on the moon.
Right.
Assuming we went there. No, just kidding. Just kidding.
India just verified it yet again.
Yeah.
Another orbiter with photos of the lander and everything. But
Yep. But
so, yeah, we can get into that talk. I have a bad habit.
prefer not to.
The Earth is also round.
Right.
I can guarantee you that.
That'll fill up the
So this-
chat.
Yep. This is a photo of Mount Wilson. You see that what's nice with the array is it's hidden in with all these historic telescopes, these solar towers, the 60-inch telescope, the 100-inch telescope. But there's a couple of these domes in here, 6 of them, that are our array. And yeah, it's able to resolve just right now, like the current generation of the array, 200 microarc seconds. So that's the size of a nickel from 10,000 miles away, or the size of an astronaut's head on the moon.
Now I'm going to interject here to say
Please.
that so that people understand, you would not see the nickel at that distance.
Right.
What you would be seeing through an array is actually a set of fringes, a set of interference patterns. And so it takes a little bit more to get put together
There's a
a
finesse
picture.
to it.
Yeah.
Yeah, we could measure with just 2 telescopes. You can measure a diameter. So assuming, and I'm playing a little hand wavy. I'm assuming we have the contrast. You know, a nickel would need to be very, very bright for us to see it that far away.
Right.
But the resolution, what we are measuring mostly is stars. And since the stars are incredibly bright and incredibly far away, they appear about that size of, a nickel from 10,000 miles. And we can measure the diameter of that star. Now, when we add in, we have, I said we only need 2 telescopes. Why do we have more? Every telescope you add in, there's different combinations between all the others. So if you have, 2 telescopes, you can draw 1 line between them. If you have 3 telescopes, you can draw 3 lines between all of them. You keep going up, you can draw more and more lines. And with 6 telescopes, you can draw 15, what we call baselines between them. Now, when you do that, you're able to actually build an image. So we measure fringes, but we can reconstruct images. And really what you're doing with a normal single aperture, single mirror telescope is the same thing. An image is being produced through interference and through patterns, through what's called a Fourier transform, which is a math trick, but it's real. And they were able to produce this image. So it's not any different. It's just like we're doing it. It's a cookie cutter thing. We're doing just the pieces that we care about to get the data we need, because we don't need to always fill in every detail.
Right.
I know back several decades ago, they used to use this trick where you put like an occulting mask in front of the telescope and have 2 openings, and then use that light passing through those 2 openings to be able to put some limits on the diameter of like supergiant stars that are nearby, these kind of things.
Yep.
Exactly. That's aperture masking. That's there's actually an instrument that does that on the James Webb Space Telescope as well.
Right.
Okay, cool.
And the first interferometry, when I showed that first picture of the 100-inch telescope, the first interferometer was done on that. We have it in our museum as basically a big 20-foot wide iron beam with 2 outrigger mirrors on it. And it was basically like outriggers put on the top of the telescope to catch light from 20 feet apart instead of the 100-inch diameter of the mirror. And so with that, they were able in 1920, Michelson and Pease were able to measure the diameter of Betelgeuse. So that was the first time measuring diameter of a star other than the sun.
That's
And we've
crazy.
Continued that on. I'm going to talk about this one. This just shows, so this first image, where'd it go? This one shows like that extremely large telescope, the 30-meter telescope. This is one of those Gemini telescopes here, the circle, just to give you the scale. And there's a human here and a basketball court. CHARA's telescopes are only 1 meter. So our telescopes themselves are not very big. But what I've truncated is the distance between them. When you actually put it to scale with the separation, then you see these blue lines. This is the size of the CHARA array. And this is it compared to a couple other interferometers in the world. There's not many. There's one in the Southern Hemisphere called the VLTI. And there's also one called NPOI, also in the US. But CHARA has got the longest baseline, the longest separation between these. And that gives us the highest resolution of any instrument in the world.
Nice.
So Nick, the way they're situated, I mean, like the VLA and Socorro, New Mexico is a Y-shaped pattern also. So that must maximize your contrast given the number of receivers that you have, telescopes in your system to cover, what is that, UV visibility plane that they call it?
Yep. You want to cover, it's called UV coverage. The plane, your separation of your telescopes is projected onto the sky. And if you imagine a disk on the sky that's your star that you want to resolve or image, you want to have those projections of the baseline crossing it in different directions. You want to do non-redundant. You don't want to copy and have just a line. So if you have just a line across it, you can measure the diameter and that's it. But what if it's longer in one axis than the other? You draw another line. And then what if it's, not necessarily spherically symmetric and you want to have more lines? The more lines you have, the more you can start to build up that image. So that's part of that trick that goes into going from fringes to creating an image, is to have really good UV sampling.
And then you would also compensate for the rotation of the Earth during your observations, right? If you're making long observations.
Oh, we're getting to that. Yeah.
Okay. I don't want to spoil it.
No, you're right. You lead up perfectly to the next slide. So your audience, almost everyone should know that, a telescope, if you just point it at the star in the night, if it's like a little like Dobsonian, you look at it, you look away for surprisingly short amount of time. Like take a minute and look away, you look back and the star is gone. You compensate for this by having a clock drive, right? So the star is moving because the Earth's rotating. Yet again, the Earth isn't flat. We do rotate in space. So you put a clock in your telescope, and that is connected to a motor, and then that compensates for the Earth's rotation, and then you can sit there and take long exposures. We've had this technology for centuries. So there's an extra step if you're doing interferometry, because go back to when I said like light's a wave, to capture that, the main thing you have to do with an interferometer is get your light to all arrive at your camera at the exact same time. It's all about timing. And in our case, we can't control the speed of light, but we can give it more distance to travel. So in this case, with this little diagram, we've got a star off to the left, depending on if the image is mirrored or not, off to one side. Both telescopes have their clock drives and they're pointing at the same star. But unless you're pointing straight up, the light from the star is going to hit one telescope before it hits the other telescope. And if you start a stopwatch when the light hits the first telescope, and you stop it when the light hits the second telescope, that's the delay. That's the time we have to take up. And we think of it in terms of space, because we can't change the time for light. It's traveling through medium at its fixed rate. But what we can do is measure that delay. And for that beam where that went through the first telescope, we give it more distance to travel. So we have it do a lap. And what we have is this optical path length compensation. And what I think of it as is an optical trombone, right? Change the sound of a trombone, you pull the slide out, you give it the air more distance to travel, it changes the pitch. With us, the light's all traveling at one speed. The one we want to slow down, we give it more distance to travel, and then we time it and measure that distance so precisely that the same photon hits the detector at the same time. So that if it's a wave, it goes through all those paths at once and it all ends up at the same place at the exact same time. And Rob mentioned the fringes. This is what fringes look like. And it is just squiggly lines. We do a lot with squiggly lines in interferometry. And you start to really appreciate and love these squiggly lines. Because the only way to get them is if you get that distance exactly right and you get this interference. Otherwise, you'll never get it. So there's one like sweet spot where you're moving something. Remember the array, the widest separation between the telescopes is 331 meters. So you're like 1,000 feet. More than that. By the time it's in the lab, we're compensating for that distance down to fractions of a wavelength. So less than a micron.
Wow. And so, I will sit there and say, having seen this process at work, it's basically these trolley cars with mirrors on them that are sliding around on rails.
I will show you some pictures of them and we'll talk about them, because the Opal carts are amazing. So we love our acronyms in astronomy. So it's optical path length equalization becomes Opal.
So Nick, in the generation of the signal that you show, that fringe pattern, so you want to bring the photons in such a way that they constructively interfere. Is that true?
We get both. We get constructive and destructive, right? Well, that's the fringes, is the light and dark. We're seeing that pattern.
So if you bring in light from, let's say, a certain star, what's that delay get you? Because you're not going to detect the same photon, obviously, right? It's coming in one detector and a different photon is coming in another detector that's separated by several meters. I'm thinking of the separation of two telescopes.
Sure. There is an interferometry that does that, where it's separate photons. That is intensity interferometry. This is different. Another way to think about it, which is the harder way, because human brains are limited, it's not a different photon. It's the wave going through every telescope at once and then meeting itself and interfering with itself.
Okay. So it's
There are no
quantum
photons.
mechanical properties.
It has quantum mechanical properties.
Okay.
The more proper way to think of it is that way, but that's also the harder way to think of it. But it is
Yes.
the same photon. It's not a photon until it's the detector. It's the same wavefront coming in and taking all paths. And only when that distance is exactly right, you're letting the wave meet up with itself. And then with slight variations in that delay, you get constructive or destructive interference.
So in other
We
words,
actually scan through the distance to get that.
right? So you should be thinking as the particle-like nature, like bundles of energy being photons. In this case, strictly the Huygens interpretation, right? Wavefronts.
Mm-hmm.
Now, is this related to, and I believe this is true or not, that the Keck telescopes, one of the things for building a second one was that the hope was to combine the two together as an interferometer, optical interferometer, or / near infrared interferometer. But that never worked after many years of trying. So would that be more of individual, like separate photons coming in and trying to somehow combine that? Would that be the technique that CHARA is using?
It was the CHARA technique, the Michelson interferometer technique. I don't know the exact details of that one, but they were trying to interfere light from the same light going to the same place.
I guess I'm thinking, what is the difficulty of CHARA is able to do it, and yet the Keck wasn't able to? And I think NASA or somebody dropped the funding after a while and said, we'll wait for time to go by so the techniques get developed better or something, right?
Interferometry is incredibly difficult. It is very easy to not get fringes.
Right.
Like there's many ways that it can be incredibly difficult. And CHARA has been remarkably successful with very limited but talented resources. Like I like to explain to people, like if you're taking data and a car drives by in the parking lot, we will see it. You know, if you walk through the lab, you'll lose fringes because of the vibration of people's footsteps. And the lab has concrete slabs that are 3 feet thick. The lab is actually a building within a building. I'll get to that. Like we keep it temperature controlled. Like the amount of stability needed is just mind boggling.
Right. Like you said earlier, you've got to get down to the path lengths down to fractions of the wavelength. And these wavelengths are 600 nanometers.
600. Yeah. We work from R band through infrared. So visible to like kind of green to near infrared.
Right.
I just wonder where the Keck telescopes, their design is unique when it was built, and you made up to these smaller, and I think of it like a jigsaw puzzle put together, but you have to actively control the shape of those mirrors. So there seems like there's a lot more dynamical stuff going on with the Keck than a single solid, like 1 meter diameter mirror blank, and that must add in some complications to the whole system.
Sure. The main thing that'll kill you in interferometry is vibration.
Right.
And I don't know the details of why Keck struggled. There's probably numerous, and not to downplay their efforts, but like it is the slightest vibration will throw you, and everything is moving all of the time. There's 2 things I've learned from doing optics for a very long time. Everything is dirtier than you think, and everything is moving all the time.
Right.
I just think, do you want to put it somewhere like, hopefully an extinct volcano like Mauna Kea, where you might have a lot of tremors versus somewhere else where geology is more stable, but is there a way of isolate that anyways?
Yeah. At these levels, like you really just have to make your building as vibration isolated as possible.
Okay.
And I mean, the slightest thing, I mean, we had, like Rob said, we've got vacuum lines. I'll get to them, and vibration from your vacuum pump can transfer into the lab. And we've had that happen before. And, weird, a lot of my favorite and stressful part of my job is the troubleshooting of had a vibration at 60 hertz that was taking power away from the fringes and making things not look right. And 60 hertz, you're like, oh, it's got to be electrical. And this turned out tracing through with a very precise accelerometer that Nope. This was actually the vacuum pump outside had been mounted on different springs than normal, and it was transmitting, and it just happened to be resonant at exactly 60 hertz, which happens to be the same frequency that all of our electricity is at. And so looked electrical, but was actually mechanical.
Well, Nick, it sounds like there would be a huge benefit if you're not doing this already to like be in collaboration with the LIGO people.
We're not in collaboration with them, but they do very similar things, and they're designed very similar. You know, it's the same type of thing. It's a Michelson interferometer.
Yeah.
Right.
Yeah.
And just to throw in experience in a physics lab, we have our undergraduates go through and build a Michelson interferometer, which does much the same thing. And when the faculty and staff were putting it together to show that it would work ourselves, that it would work, we'd breathe on the beam path and you could see the fringes shift. So Nick is not kidding, folks. These things are incredibly sensitive to a ridiculous level.
There's two things if you want to torture a student, like, and scare them early on, and give them build in an interferometer, like just a little Michelson tabletop one, or what was it? Was it the which was the experiment with the charge ratio of E, where you've got to watch the oil drops?
The Michelson.
Michelson,
oil drop.
Millikan oil drop.
Yeah. Millikan oil drop. The Millikan oil drop. And then later was found that like he may not have actually seen the results.
Yes, I heard that.
Yeah.
And I'm like, that was so vindicating because that was the only one in modern physics. I'm like, I don't see any difference. They're just oil drops moving in random.
Right.
I did do that one.
Yeah. So it's up there in the difficulty. Right. So this is one of our telescopes. This is our 1 meter telescope, custom built to be as rigid as possible. So even at the telescope level, we have custom design. So nice. One of the unique features of this is these rods. There's 4 rods, one at each corner. And it's got this square frame instead of round because every telescope is always a cylinder. These 4 rods are made of Invar. So Invar is an alloy of steel that has a very, very low coefficient of expansion, meaning that this rod doesn't expand and contract when it gets hot and cold like every other metal. And the telescope is actually, this truss pulls it all tight against those Invar beams. And those Invar rods hold the focal distance between the secondary mirror at the top here and the primary at the bottom. If you're not familiar with telescopes, we count the mirrors. The primary is the first one, secondary is the second one. Then we go M3 in the middle, which kicks the light out to the side. And I'll go through some of the mirrors at CHARA. One of the challenges that we trade off sensitivity because we've got to move the light around a lot, which means a lot of reflections. And every reflection, even if your coating's perfect, is at best 98%, maybe 99. But if you have 20 reflections, 0.99 raised to the 20th power, you're losing a lot of light.
Yeah. So these are like Kute type focus telescopes?
They're Mersenne. They actually don't have a focus. So they're the Mersenne design. We also have some telescope that's a Ritchie creation that does come to a focus. I'll talk about that if we want later. But yeah, it's a beam reducer. So the beam comes in at 1 meter, and the only powered optics at this point are the primary and the secondary. Everything else going all the way into the lab is a flat mirror. So the only ones that have curvature are the primary and the secondary. And all it does is bring the beam from 1 meter and shrink it down to a cylinder that's 12.5 centimeters wide.
So how does that get transmitted? Just through a evacuated tunnel?
Exactly.
Okay.
So we got M3 here, kicks it off to the side where we have a 4th mirror, which is our deformable mirror because we have an adaptive optics system, which is something else I can talk about that's also really hard to do. At the bottom of that, we have M5. That kicks it back under the telescope where we have M6. That sends it all the way down because you noticed it's elevated and all the telescopes are at the same height. M6 kicks it down to M7. Some telescopes have an M8 and M9. Then it goes into a vacuum window. And then because a lot of the turbulence in the air is at the ground level, that's why we put it all in pipes that are in vacuum. So from then it goes all the way to the lab along the baseline through these vacuum tubes.
Now, what about wind? I mean, that obviously would limit when you're pointing at certain things, with the wind's coming in through the slit of the dome.
Yeah. We have limits for when we can operate in wind. If you have wind hitting the telescope, it'll cause it to vibrate and your fringes will move.
Yeah. Okay.
So we have limitations for that, and we don't open if the winds are too high. So this is that path. So the beam comes in, bounces around, goes through the coude, which is French for elbow. That's that bend around here, and then goes into the pipes. And from there, it goes into the lab. I'll talk about the AO system if we want to go into that rabbit hole later. But this is the lab, part of it. And this is where the light comes. there's more mirrors in vacuum turning boxes, which are these big cylinders that we get the light all lined up because it's all coming in from different angles, that Y-shape array. And we get all the beams lined up in order, so it's nice in this long building. And then we have this super long building. It actually extends past that back wall, another, I think, 40 meters. We've got about 45 meters here of active delay. Underneath the active delay, there's these kind of bulkheads here. There's mirrors there that can go in and out on a motorized stage. Based on where we're looking in the sky, we can do bulk delay. So just, like it's like a patch cable. We know, oh, we're looking over here. We only need this much delay. We can take that out because the carts have a limited range in which they can run. And depending on where you're looking, it'll change how fast they're going because they have to match the rate at which the sky is turning, appearing to turn. So light comes down, hits these carts. If the carts then bounces back to where we have the instruments. So this is what the cart looks like. At the back, you got a motor that drives it along a metal rail. So metal wheel on a metal rail. It's not actually physically touching the cart that it's pushing. It's on a voice coil. So it's like a big old school speaker where it's a speaker coil and the electromagnetically couples with the cart. So that's our first stage, not have vibration transferring from the motor that's moving to the cart that's just rolling on these kinematic rails. These rails are aligned to fractions of a millimeter, really getting into like several micron range.
Wow.
Then you've got a mirror here on the back of the cart, which is on another voice coil. And that's the one that is moving in and out to do the first stage of correction. Well, really a second stage of correction for the delay. The cart's position is the 0th order. Moving the mirror is the next step. And then at the tip here, hidden in the metal, there's a cat's eye reflector, which is, it's just like the telescope. You got primary, secondary, and then the light bounces back out in this case. In there, you've got a cat's eye reflector that's on a little piezo. And piezo is a quartz crystal that when you apply electricity to it, it changes its shape. So on that piezo stack, you can change the position of that mirror. And at that point, you're now getting into like sub-micron precision. At the same time as all of this, we've got an infrared laser that's bouncing on off the cart and telling us exactly where the cart is with another interferometer.
Now, the room that all this stuff is in, that must be like environmentally controlled
Nope.
as best as possible.
These walls are the inner walls. There's actually a corridor that you can walk down all the way around this. So this is a building within a building. And then there's like 2 feet of big, fiberglass insulation around all of it. It's on these really massive concrete slabs, which are all gapped so that they're not transmitting vibration from one to the next. It's really a feat of engineering.
And it is a clean room, if I remember correctly, too. So
Clean-ish. We don't do the full bunny suits, but put on booties on your shoes so you're not tracking in dust. We try to keep it as isolated as possible, but not a proper full clean room where you gotta, put on the bunny suit, put on the hair cap and all that.
What about temperature variations in that room? Is that kept to a minimum? Plus,
Yep.
you use material that doesn't really respond hugely to temperature changes, I assume, right?
We try to keep that room at about 68, 70 degrees all the time.
Okay.
Just keep it stable. So now you've got 6 different telescopes, 6 beams, all lined up. And now at this point, path is equalized. So the light's traveled, you've got wavefronts, they're all equalized. The light has traveled the exact same distance. Now you get into the fun bit of getting it where you want it to go. This is actually an older image. This table is even more busy now. This is where the laser is sent out. But in general, the light comes in. First thing we do is shrink it. Just like at the telescopes. This is another powered optic. It's just a little beam reducing telescope for 2 reasons. One, the smaller your optics are, the cheaper they are.
Right.
And 2, and we've got a lot of optics. 2, we've got to fit these much more compactly now. So we don't have room to have big optics. So we got to shrink everything down. And so that's done at this stage. This makes the beam a 19 millimeter beam, so a little less than an inch. One of the ways I describe this, if you're working on it, like especially when I talk to do outreach, is this is like working with the most expensive Lego set in the world. It's great. Because on this optical bench and with these clamps, you can machine mounts, you can put stuff. These are all designed so that they don't expand and contract a lot, that they're incredibly rigid, they're stable. Some of them are floating on gas pressure so that they're isolated from the ground. There's all these things you can do with optical tables. It's really cool. And it just lets you precisely position your optics. At this point, we've got another deformable mirror, another adaptive optics set, which corrects for all the aberrations that come in from imperfections in your mirrors after all these reflections. Because notice these mirrors are adding up. We've had a lot of reflections. And then in the back here, where I've changed the color from yellow to blue and red, is that we've got it's called a dichroic, which is like a beam splitter, and a mirror. So we split off here the visible light and, on the bluer end from the infrared light on the red end. And so now at this point, coming out of this part of the lab, going into this other beam combining room, we've got 6 visible beams, all path corrected, and 6 infrared beams, all path corrected. And what this does is then go to the different instruments. And we have many different instruments.
So what's the advantage of blue versus infrared? So like the diffraction limit, you want to keep the wavelength as short as possible to give you the highest resolution.
Yep.
It's just that would, if you go to infrared, that would increase your target selection. That would be more information, I guess, from those wavelengths than the shorter wavelengths.
Yep, different science cases based on what you're looking at, whether you think is emitting infrared. Downside of infrared is that you're also, and the lab is glowing in the bands we're looking at. So like K band and H band, most things are emitting light in that. So that becomes a challenge. Bluer you are, you're right, the higher resolution, but then bluer is also harder to do. So there's trade-offs for each. And what's really nice about CHARA is what GSU did was get CHARA built, get the array built, and build one beam combiner, just CHARA Classic. And it is just a straightforward Michelson beam combiner. You get all these beams and you send them in, get 2 beams and send them into a camera. That's all Classic did. What we then did was invite in collaboration. And different schools and different organizations and different countries and different universities, all, or different groups of researchers, all contributed different things to the array. And so we have this very nice, very full lab. Basically, each one of these tables is a different instrument. So on this front table, we've got University of Michigan with MERC-X and MYSTIC. So that's the H-band and K-band imaging interferometers. So these take all 6 beams in the infrared, where there are 2 different bands of it, and build images. I can show you some images we've made, and that's what it's for.
So that would that would allow you to probe, if you're looking at a star, for example, probe into different layers of its atmosphere, depending on the filter, essentially, right? The wavelength that you're concentrating on.
Yeah, it's seeing different parts of the star. Like you're seeing resolving the surfaces really well with that. That's where we produce like stellar images of especially giant stars, red stars. It's also looking at like accretion disks, and planetary formation is a big science driver for it. So looking at, you've got hot dust around a star that's emitting thermal radiation. That's what this is going to help with.
Okay.
For the visible end, we've got the newest combiner, Spica, or one of the newest combiners, Spica, which is out of our French group, our colleagues at the Côte d'Azur in Nice. They've built basically a 6-beam combiner that does similar to what MERC-X does, but does it in the R band.
Oh, wow.
What's really cool about CHARA is this is built that these can run simultaneously. So MERC-X in the H band and MYSTIC in the K band and Spica in the R band can all work at the same time if looking at the same object, and you get all 3 colors at the same time and get images in all 3, or get spectral features in all 3, depending, because they also have different prisms or grisms, so you can get spectral information at the same time.
Sweet.
So the amount of data is insane.
Yes. But at the same time, wow. I mean, that will tell you so much about what you're looking at. Now I remember, we're talking about the lowercase g, gravitational acceleration, pressure, densities, all that type of stuff.
Metallicity,
in the atmosphere, metallicity.
Astroseismology. So actually verifying this technique where you can see the sound waves propagating through a star, leading it to have pulsations that show up in the light. We can do that. There's a huge list of the type of science we can do.
So what's the limit in terms of apparent magnitude, let's say in the V band, roughly?
V band, we don't have any science instruments, but our V band limit is our tip tilt and our tracking and our different mirrors for the AO system. And that's like, I think 12 to 14 in V.
Okay.
For imaging, actually, I think I have a slide that has or I can get it for you, the table of all the different instruments. They each one have different limiting magnitudes.
Right.
But something don't quote me on, but I think like with H and K, it's around 8 point something.
Right.
With Classic, we've gotten to over 9, which means we've started to get AGN. So active galactic nuclei, not just limited to stars. We've done science on the supermassive black holes at the core of other galaxies.
Now, if you add more, let's say someone comes up and I have all this money, I want to increase the number of optical...
You're my new best friend.
Optical telescopes. So clearly you have to have change a lot of the structure, right? You have to add the path lengths and all that kind of stuff to it. Will that allow you to go fainter, or will that just provide you a better signal to noise ratio of whatever you happen to look at?
Both.
Okay.
And in a great instance of foresight, when they built this building, they did put in rails for a 7th and 8th cart.
Okay.
So we have some of the infrastructure ready to expand. We actually put in a grant to do so, but the current state of the NSF leaves that very questionable
Right.
Okay.
on
So,
what'll happen.
so if I win Mega Millions tonight,
You're right. Yeah.
I'll be in
I'll name it
contact.
after you.
Oh,
We'll have
thank
the
you.
Wayne. Yeah.
The Wayne Array. The Wayne.
Wayne
the
gone
Wayne
away.
edition.
Wayne
Wayne
gone away.
edition, There we go.
No, that is actually how CHARA was originally got funded to do 5 telescopes, and on the basis because it's nonlinear. Every time you add a telescope, remember you've got more lines between all of them. So the more telescopes you have, you get an exponential increase in the amount of data you get for imaging. So GSU was going to build 5 telescopes. The Keck Foundation, on the basis of how good the imaging would become with the 6th telescope, they kicked in and bought another telescope for us.
Nice.
Okay. In case somebody's wondering, and before I forget this question, so what makes the CHARA array different than, let's say, the Event Horizon telescope, where you run off to the
Sure.
different radio telescopes and you record your signal using an atomic clock, and then you bring all that data back and run it through a correlator, I assume, to combine it. So why can't you do that with like CHARA? Why can't I have a CHARA mini set up somewhere on the East Coast of the United States or whatever?
A catch of quantum physics, unfortunately, because the timing, the frequency is related to the wavelength. When you go shorter wavelength, your timing precision has to be greater and greater. And so you get a fundamental limit when you get bluer into this like near infrared and visible, of course, that you can no longer do that because you cannot have a clock that is accurate enough at the same time having enough integration time to capture a photon.
Got it.
So there are ideas and some ways that maybe in the future things could be done, but currently there is no way to do it. And instead we have to physically combine the light. That's why we have this kind of Dr. Seussian mad kaleidoscope trombone thing to make it all work.
Yeah.
Which makes it an engineering marvel. But yeah, people often ask if they're familiar. The trade-off, though, this is a lot more work. The Event Horizon telescope, amazing images of the black holes and Event Horizon. That's great. It took telescopes across the entire diameter of the Earth to get that baseline to make that image. If you account for the wavelength, their resolution is the same as ours.
Wow.
What we do on one mountaintop is the same resolution as the entire diameter of the Earth because they were in much longer wavelength.
Much longer. Right.
Right. Yeah.
Right.
So
And the other thing is, in the future, you could take CHARA-like and make it space-based.
there's been thoughts on doing an interferometer in space. There are several challenges. You need to master formation flying, which is yet to be demonstrated very well in space. That was a limiting thing. Or you make it a single beam and make it larger. There was plans like SIM to do that and SIM Light. It's promising, but yet to be done. There's plans to put an interferometer on the moon. There's lots of things to talk about doing it, but really actually doing it. And I'm a big fan of ground-based because you can continually upgrade.
Right.
If you look at like how CHARA was originally built, some of our detectors were, things from engineering grade chips from a drawer in NOAO that were loaned to us, and, old picnic detectors that were similar to what's used on Hubble, which is 30 years old. Now we have multiple state-of-the-art, it's called CRED-1 cameras. We have photon counting detectors, like they're sensitive to a single photon in the infrared, and we have ones that are sensitive to photons in the visible. So we've been able to continually upgrade the array, and that's something you can only do ground-based.
Right.
We've also built this consortium. We have a huge number of collaborators now, and that's because they could send their students. They could offer to build an instrument. Like one of our newest is this Chariot. Chariot is the 3rd instrument to be on this table because we can do that on the ground. And it was first the Fluor instrument, and then became JoFlu, and that's what I wrote my dissertation on. And when it broke and finally died, we got new collaborators and put another thing on top of it.
I can see the benefit, like at LISA, the prototype that the European Space Agency had sent up after the first detection of gravitational waves, and so that obviously got people's attention, and then funding agencies kind of looked towards that. So, but it's it's at the very, very early stage of flying it, like you mentioned, in formation. So any benefit any information they can provide, of course, would be great benefit for future CHARA like instruments.
Yeah. No, I mean in a not budget limited science world, we would do both.
Yeah.
But really, just nothing beats ground based as far as what you can do. And again, there's so many subsystems that work. That's one of the things I think it's taken a long time to ever get an interferometer in space. Is there are many, many ways it can break. You've got a
Right.
lot of moving parts, and space agencies do not like moving parts.
Yeah.
I wonder why.
Yeah.
Yeah. That's why you hold your breath when they launch James Webb, right?
Right.
Yep.
Yeah.
Let's see, I'm gonna skip that. So I talked about Chariot. Just to give you an example of like a simple instrument. Chariot is one that I just started working on. It's a new collaboration with the Leibniz Institute for Astrophysics in Potsdam, Germany, along with some in the UK, working with someone in Edinburgh. So it's a big team. This is 3 of them there. This is on the left, Narcy, one of the CHARA scientists, and myself. This is our first fringes. First fringes, you get to have champagne, and you're right on the bottle and sign it, and it goes on the wall. Nice perk. This is a really simple idea of, well, we had all this stuff for this previous beam combiner where the camera died, but it had all these fiber injectors, it had the optics, it had stages that can control. Because what you do is once you get the light even, one of the ways you can measure the fringes is you just change the path a little bit. You get a little stage that just moves a mirror, wiggles it back and forth, and you'll see, bands of light, dark, light, dark, light, dark. And that's what you measure. Measuring the contrast between the light and dark is what tells you everything. I can explain that if we want to go really into the weeds, but basically, measuring contrast is related to the diameter of the object you're measuring.
Right.
And if you do that many different ways, well, if you measure a bunch of diameters at different scales and put them all together from different scales in different directions, that's kind of what an image is, right?
Right. We do have a question, so I'm going to interrupt you
Sure.
here.
Please.
We have St. German asking, I wonder if they use any relays. Now, I'm not 100% sure what they're asking, but
Relay optics or relays as in turning power on and off remotely. We
Right.
do that. We do both. Relay optics would be the whole beam train. If you mean relays like remotely turning things on and off, all the telescopes are remotely controlled from this office right here. The
Nice.
array can be run by one person at night.
How
Usually
often,
someone on call and helping, but
I was gonna say, how often do things like break down?
with the number of subsystems and stuff, constantly.
Okay.
That is the main part of my job. I am a telescope system scientist. That is everything outside of the lab. If it breaks, it's on me to fix it.
And
Thankfully, we all have many hats, and I usually pull in other people to help because no one person can do all of it. And same with the lab. There's someone else who, if it breaks in the lab, it's their job to figure out who to pull to help and to get it working by night. But during the night, it's always, I started out as a CHARA array operator while I was in grad school. So I finished my PhD while working nights running the array. And it always amazed me how well it does work.
And we've got another question
Sure.
from a former professor here. He's, I'm wondering about the effect of adding another telescope. Isn't it quadratic rather than exponential?
As far as number of baselines, yeah, I think I was talking hyperbolically, but if you want to go like number of baselines, it's n times n minus 1 over 2. So if you have 6 telescopes, it's 6 times 5 is 30 divided by 2, 15 baselines. If you had another, it'd be 7 times 6, so 42, so you get 21. So it goes from 15 to 21. Not technically, yeah, you're correct.
So you could think of that as like a one-dimensional sampling of an image.
Yep.
And you obviously don't want to sample at the exact same location. So the more spread out, the more information you're going to get, like spatial
You want
information.
a non-redundant array.
Yeah.
And you do the same thing with aperture masking. You can do it with the multi-segmented telescopes where they just intentionally misalign some of the mirrors, and then you basically made an aperture mask.
Right.
Nice.
Yeah, feel free to interrupt anytime. I'll just keep babbling.
Okay.
Chariot's really cool because it's the CHARA array integrated optics test bed. And what we decided is like, well, we've got all the stuff to inject light into fibers, and the fiber combiner eventually, aged out and died. It got some polarization effects because the fibers separated and it was not salvageable anymore. And so opened it up to this collaboration. And what we did is this is an optics group that do not work on sky. This is their first time using telescopes for science and all that. And what they did is, well, we build integrated optics. We'd like to test them on sky and stuff we've been trying in the lab. So they use, laser etching inside these substrates of like infrasil and in this type of glass to make little chips that the light goes through. So this is photonics. And what we did is built this to be able to just plug and play your interferometer and test it. So we've got a new camera, a new output stage. We're eventually going to have 4 beams. Currently, it's only 2. But then anyone could just, this opens up to many, many different universities and labs. And like, hey, I'm testing this new thing. This is what it looks like. Here, can I come and plug it in and try it on Sky? Sure.
Nice.
What about the benefit to like the military?
The military has invested in an interferometer, one at Magdalena Ridge, which has been under construction for a while. The military has interest in imaging satellites, like imaging imaging Chinese satellites, what type of payloads they have, what they might be doing, that sort of reconnaissance. And they have their own interferometers. CHARA has stayed purely scientific.
Okay. Because I know, people try to take an image of like the International Space Station. So you take a very short exposure and take a lot of them, just pick out the ones.
Oh, it's lucky imaging.
Yeah, with best seeing, and you then stack those together type of thing.
So the other science and instruments I do is speckle imaging, which people often confuse for lucky. Speckle is also interferometry, but you take a lot of very fast images, so fast that you freeze the atmosphere, and the atmosphere itself, the turbulence within it, creates your difference in path lengths and causes interference. You get a speckle pattern. And from that, you can then create an image, usually binary stars, and see, oh, actually, this looked like one star, but there's really two there. And you can get a diffraction limited image from an 8-meter telescope. That's why I was at Gemini. So at Gemini North and Gemini South, we have diffraction limited imaging with two instruments called Alipeke and Zorro, which are speckle imagers.
Okay.
But I often have to explain to people, it's not lucky imaging just because you're going fast. Lucky imaging, you throw away 99% of your images. With speckle, you actually keep all that data and you integrate it, and you do the Fourier transforms, and you do the math, and you get a diffraction limit images out.
Yeah, because the lucky stuff, you're kind of limited to how faint you can go, because if you take a very short exposures, if it's not bright enough to register a single photon, what's the use of it, right?
Yep. Where with speckle, you're leveraging the interferometry part, and it's really fun, even by eye. You can see, you can look at the camera reading live, and once you're used to staring at fringes a lot, you'll see it looks kind of like a herringbone, like fringy pattern, and you're like, oh yeah, that's a double, and the orientation is this way, and separation is probably this, just by looking at raw fringes.
Right.
Interesting. Yeah, remind me of like the old days when they looked at spectra and said, yeah, there's a spectroscopic binary, right?
Right.
Yeah. Yeah.
And
I love it. It feels like you're actually doing like real astronomy, right? Like seat of your pants, like you need the pipe and the whole thing. Ah, yeah, that's your double.
Or like me with what I've done is the photometry. You're looking at 3 columns of numbers, and you're able to go after a little while, go, yep, something happened here. Even before you do the analysis, the math.
Yeah, humans are amazing at pattern matching.
Right.
Yeah, that's why we always design computer code to find objects that try to match it to the eye as best as possible.
Yep.
Yeah. So this is a satellite image of Mount Wilson. The red dots are where the current array is. I've added a green dot here, here, and here. And there's some little ones we'll talk about, but these big green dots, these 3, are our newest addition. We've built a mobile 1-meter telescope, and it can go to, currently it's at this spot. It will then go to this spot, and later it will move between them. And ultimately we want to get it out to here. What this does is we've made another little triangle, and this is connected by optical fiber instead of the long beam train. So we're testing out using multiple sections of, I think, roughly 600 meter long fiber, and putting the light from the telescope into that. And then that goes to the rails at the cart, and then goes to the same instruments.
Oh,
so we can actually add a 7th telescope in. This gives us a 17-meter baseline, which actually having a shorter baseline is kind of nice. It lets us look at more extended objects. So it fills in some UV coverage for us and some spatial resolution. And then once it goes to here, we'll have a 550-meter baseline, which then makes us even more the largest interferometer in the world, roughly doubles our resolution. And ultimately, we have most of the things we need. We need to do some site prep, but as far as the fibers and all of that and trenching based on these experiments and how well these go, we have gotten lab fringes through these fibers. Not got them on Sky yet. The fire delayed us, but sometime early this year, we will get starlight fringes through these fibers, and that will be a first. And ultimately, this would be an 1,100-meter baseline. So we'll triple our resolution.
Why not go to the longest baseline immediately? Why do the shorter
It's harder.
one? Okay.
Longer is always harder. Yeah, the longer your baseline, the harder it is. The more dispersion you have through your fibers, which is challenge with fibers is you get spectral dispersion through them, more vibration, longer trenching, anything that could be messing it up. You also more loss of light. So you really let's start easy and go up the staircase.
So you just develop that technology as you go along then.
Right.
Yep.
And
And
the
this is of a lot of
expertise.
interest. Yeah.
Okay.
And the
And
expertise.
really, this is, state of the art for the world type expertise. VLTI has worked on fibers. There's many experts like I was at a conference recently with many of them of putting optics, doing interferometry through fibers. It was done on Mauna Kea called the Ohana project for a little bit, but that also kind of didn't really get invested in like it could have. And the VLTI, the Very Large Telescope Array, they have 4 very large telescopes that can be hooked up together that are 8-meter class. And then they have these auxiliary telescopes that I think are 1.6. Don't quote me if I'm wrong, somewhere around 1.5 meters, that they can move, and they can combine an interferometer that's been very successful with many instruments like MIDI, Pioneer, Gravity.
Yeah.
And they've been doing, using optical fibers too. And so we want to start combining our telescopes with the optical fiber over long baselines.
Has there been any development like in optical fiber technology over the years?
I mean, tons. The challenge is we don't work in telecom wavebands. So we don't have the same level of development. These are much more kind of bespoke custom fibers. One of our collaborators, a group called, also out of France, basically if you want to do interferometry, it's the US, Australia, or France. One of the groups out of France called Aloha, they did some tests between our S1 and S2 telescopes where they put light into fibers. And what they did is up conversion. So using nonlinear crystals, you take the infrared light, you use a pump laser, you inject more energy into the light, and some magic happens within the crystal where you get a visible light photon out. So you trade off some sensitivity, but you change the wavelength of your same light, and then you put that through telecom fibers and telecom detectors that are super sensitive and really cheap because they're used all the time. And they were able to get success in that way.
Nice.
So we've gathered a lot of expertise on putting stuff into fibers, but there's a lot to do.
And I hate to cut us off. We're going to have you back or something, Nick, because this is great. But we're up at an hour, so
it went really fast. That's for sure.
It went really fast. So thank you, because that's great.
Almost the speed of light.
Almost the speed of light.
Anytime.
So we may be talking to bring you back sometime.
Yeah, exactly.
Sure. We can schedule that out.
Yeah.
Well, if any of you are interested in this type of work, and I'm sure many of you are, then what better place to go to is to increase your education. Go to any university or college to get a degree. Or degrees with a plural.
Plural.
Yep.
Including coming here at the University of North Dakota. We have both online and on-campus courses that you are able to take, hopefully. And if you are around, drop in to see Rob and I.
Yes, indeed. Come by and see us.
If you're interested in CHARA, we can kind of steer you towards Nick a little bit.
Absolutely.
CHARA.gsu.edu is our website. And then if you're in the LA area, like it's open to the public to come take a look at Mount Wilson during the daytime.
Yeah, go for a visit.
We have a little museum, yeah.
Feed the squirrels while you're there.
They're large enough.
And watch out for the pine cones.
Yep.
Yeah. Our next podcast will be next Tuesday on February the 25th. We always leave you with a quote at the end of the podcast. So this quote is related. So it's actually from a presentation that was given in 1801. Let's see if you guys can know the person. 1801 should give it away immediately. But the presentation was given to the Royal Society of London. And it's by, and you want to take a crack at it?
I'm not going to take a crack at it.
1801, Nick, Thomas Young.
Okay.
And so here's the quote. It has been shown that 2 equal series of waves proceeding from centers near each other may be seen to destroy each other's effects at certain points, destructive interference, and at other points to redouble them, destructive interference. And the beating of 2 sounds has been explained from a similar interference. So Thomas Young, famous for the double slit experiment, of course.
Yep.
That we know and love. So anyways, if you like this podcast, please remember to give us a thumbs up, subscribe if you haven't subscribed, and thank you for watching.
Thank you, folks. We'll see you next week.
Thanks, guys.